Okay, here we are doing answers for on paper first exam for CS202 fall 2015. Okay, and we're on question 5, the data structures chart. Okay, so for each of these, we're supposed to put the best and worst case behavior. So just the running time. We're not looking for the descriptions here. It's just the best and worst case running time. And I'm going to put best and worst. Okay, so in that order. Okay, so let's do a lookup first. That's one of the easier ones to do. So for a sorted array, what's the best case time for lookup? It's order 1, and that happens if the first item you look for is the one you're looking for. So if the item you're looking for happens to be at the midpoint of the array, the sorted array, that's the first place it looks at, and that will be order 1. For an unsorted array, where does an item need to be for you to find it quickly? At the front of the array, if you're looking through from the front to the back. Linked list for lookup, same thing. If the first place you look at has the item, then that's constant. Stack and queue, you don't necessarily normally do a lookup. You'd normally be just dealing with one end of the stack or queue, but if you wanted to look inside of the stack or queue for an item, you would have the same behavior. And also for a hash table. So for all of these, the first one you look at, if that's the one you're looking for, then that's your running time. Binary search tree can be maintained as balanced or not necessarily balanced. And so for these, which item is the first one you're going to look at? In a lookup, you're normally looking at the root. So if what you happen to look for is the root, then these would be constant time as well. All right, now let's look at, so that's best case. Maybe we'll put this here. Okay, so we'll say best. And then worst. So for a sorted array, use binary search, and the worst case running time there is log n. You divide in half and divide in half, and so on. For an unsorted array, the worst case is, people write order n. It may be more proper to write theta n, but we'll just write order n. Or we'll say n and be more efficient in our typing. Okay, so if you have to look through the entire array, for example, if you're looking for something that's not present, you won't know that unless you search through the entire array. Same thing for a linked list, same thing for a stack or queue. You're normally not necessarily doing a lookup, but if you had to, you'd have to look through the whole thing potentially. Hash table, the worst case is if all of your data items collide. If the hash value is the same on all of them, and then you're in linear worst case. For a binary search tree, it depends on whether it's balanced or not. So if your binary search tree is balanced, then the height is always order log n, and then your running time for lookup will be at most log n as well. For a not necessarily, if it's not necessarily balanced, it just depends on how unbalanced it is, and really the running time is the number of levels in the tree, or the distance between the root and the furthest leaf, which could theoretically be every node is on its own level. So for example, if you insert items into a binary search tree in increasing order, then you and you don't do anything to keep it balanced, you would have a very unbalanced tree. Okay, so that's lookup. For insert, we're doing first best and then worst. Okay, best case for in a sorted array. So for a sorted array, you have to find where the item's supposed to go and then shift everything down. Okay, and your best case that could happen there, you always have to do a lookup. So there's sort of two cases that you could think would be the best. One would be you find what you're looking for. So if you find what you're looking for right away, that's constant. But then you have to shift everything down to make room for it. So that would be like n over 2, and that would really be linear for insert. If you find what you're looking, like if you find your spot right away, if you're inserting a duplicate, for example. So another thing that can happen is, let's say you don't have to do much shifting. So for a sorted array, you always have to shift to keep things in the right order. So where would you want to insert something so that you don't have to do any shifting at all? That would be the end of the array. And then you would have log n to do the lookup to determine that you're at the end of the array, and then no shifting at all. So the running time would just be log n. Okay, so if you have a sorted array and you want to insert something that's the largest, it's going to be larger than everything, you have log n to determine that, and then you just put it at the end. Let's go ahead and do the worst case here as well. This is going to be n. So what you have to do, the worst case here would be you insert something that's smaller than the entire array. If you're inserting something that's smaller than the entire array, then you have to shift everything to the right. You also have to do a lookup, but in terms of big O, it's this linear term that is the running time. All right, let's go for a delete on sorted array. Okay, best case for a delete, and this is assuming, the question here says, assuming that we already know the thing that we want to delete. We already have a pointer to it or an index. Okay, so what's the best case for a sorted array in terms of not having to shift things over? The end. So if you want to delete the last item, if you already know that it's the last index, you don't have to do any shifting at all to delete that. You just decrease the size of the array. All right, and the worst case is, again, the first item. If you delete the first item, you fill in that empty space by shifting everything to the left. Now let's look at an unsorted array. The way you insert for an unsorted array is you always put a new item at the end of the array. So your best and your worst is the same. No matter what, you're putting the new item at the end of the array. Okay? For delete, what do we do? Let's say that we delete the last item. That's going to be constant time. You just decrease the number of items in your array. The worst case is also going to be constant, because if you already know where the thing is that you want to delete, then you take the last item and put that into the hole. So you're going to take something out. Right, you're going to take something out, so that would leave a hole. With a sorted array, you have to shift everything to keep everything in the right order. But for an unsorted array, it doesn't matter, and you can just take the last item and put that into the hole to fill it. And that's constant time. You don't have to scan through the array to do that. All right, let's look at a linked list. For inserting is very similar to an unsorted array. You insert at the head, that's constant time no matter what. That's inserting. Now for deleting. Deleting in a linked list, if you already have a pointer to the thing that you want to delete, what you do is you need to update the pointer to let's see, let's just draw a little picture here. So you have node 1, which points to node 2, which points to node 3. If those arrows are not like, this is not programming, this is just like nodes. So if I wanted to delete node 2, I need to set node 1 to point to node 3. Alright, that's a constant time thing. I don't have to look at the rest of the list to do that. So as long as we have a pointer to the previous node, then deleting in a linked list is going to be constant time. So we put a star here to say if we have a pointer to the node before the one we're deleting. Okay, and that's going to be the same for a stack. Stacks in queue can be stored with linked lists. They're going to have the same behavior as a linked list. So for inserting, which in a stack we call push constant, you just put it on the head of the linked list. For deleting, we call that in a stack a pop. And we just adjust the pointers. For a queue, inserting is called enqueue. It's also constant time. We enqueue to the tail of the linked list. As long as we keep a pointer to the tail, we're fine. For deleting, that's called dequeuing. We take off the head of a linked list, and that's just adjusting some pointers. All right, hash table. For inserting, we have to find the place in the hash table to insert this, and then it says here that if we're dealing with collisions by buckets, does it say here? Let's assume that we're dealing with collisions So what that means is we do the hash value, and anything that has the same hash value we put into a linked list. So we have a hash table. The table is a table of linked lists. So if we're inserting into a linked list, that's constant time either way. Okay, inserting is easy. It's the lookup that's the problem with linked lists, and it's the lookup that's the problem with a hash table if it doesn't behave well and everything collides. For a hash table as well, will be the same as a linked list if we already have a pointer to the thing we want to delete in the appropriate linked list. So there would be the same star here, actually, for all of these that really use a linked list underneath the covers. Okay, binary search tree that's balanced. Best case for insert. Well, if it's balanced, then the height of the tree is roughly log n, and the running time for an insert is you need to get to where you're inserting and then put it in. So this is log n to find where to insert the item, and then constant to actually update the pointers. Worst case is also log n. Okay, for a delete. So this depends on how we are defining the problem. So if we already have a pointer to the node we're trying to delete, then it's possibly just constant time. It's possibly just constant time to delete. Let's think about a leaf. If we already have a pointer to it and its parent. Okay, what's the worst that can happen? Well, I'm just going to put a question mark here because it depends on how the tree stays balanced. If you have to delete the root, then you do need to make some adjustments to fill in that gap. And we haven't talked about how we do that. So right now that's just a question mark. All right, let's look at the not necessarily balanced binary search tree. The best case for this is actually 1. If you have a completely unbalanced tree and then you insert and it ends up on the side that doesn't have any nodes, you only have to do a constant amount of work. The worst case goes the other way. If you have a completely unbalanced tree, then inserting all the way at the end is the worst. For delete with a not necessarily balanced binary search tree, definitely if we have an unbalanced tree and we need to delete something that's at a very high level and doesn't have any children, then there's not much to do there. The worst case, it depends on how delete is done. So I'll put a question mark there as well as unspecified at the moment. Okay, so that's number 5, the data structures table. For number 6, check the next video.